Hey guys, this is Megan again from OnlineMathCircle AIME video tutorial series, and today we are going to look over 2009 AIME I problem number 5. Triangle ABC has AC equal to 450 and BC equal to 300. Points K and L are located on AC and AB respectively, so that AK is equal to CK, and CL is the angle bisector of angle C. Let P be the point of intersection of BK and CL, and let M be the point on line BK for which K is the midpoint of PM. If AM is equal to 180, find LP. So first of all, let's look at the figure that I've drawn here. So we have triangle ABC, and AC is equal to 450, and BC is equal to 300. We see here that K is on AC such that AK is equal to CK, so K must be the midpoint of AC. That makes AK equal to CK equal to 450 divided by 2, which is 225, hence these marks here. And CL is the angle bisector of angle C, so we draw out point L on segment AB and connect C to L, and we see that CL bisects angle ACB, so we put the appropriate markings here. And we let P be the point of intersection of BK and CL. So we expand BK and put point P as the place where CL and BK intersect, which is right here. And M is the point on line BK for which K is the midpoint of PM. So in other words, we have to have M line BK such that PK is congruent to KM, since K is the midpoint of PM. And furthermore, we are given that AM is equal to 180 degrees. So we can mark that here. Now, another aspect of the figure we can notice here is that if we draw line segments AP and CM, we notice that we form a parallelogram AMCP. Now the question for you is, why? Well, if you look here, we see that the two diagonals are AC and PM. Look at point K. We see that K is the midpoint of AC and MP. And since AC and MP are the diagonals, they're bisected, we can conclude that AMCP must be a parallelogram, since both of its diagonals are being bisected by point K. So, therefore, AM and CP must be congruent, meaning they're both having length 180 because of the fact that they're opposite sides of the parallelogram. Now let's proceed to computing some side ratios. From the angle bisector theorem, we can look at triangle ABC, and we see that segment CL bisects angle ACB. And by the angle bisector theorem, we can conclude that AC over AL is equal to BC over BL. So in other words, 450 all over AL is equal to 300 all over BL. So the ratio of AL to BL is 450 over 300, which simplifies to 3 over 2. Next, you may be wondering, well, now we have one ratio between two line segments. Now, how do we figure out the rest? Well, there is a technique in similarities and side length ratios that's known as mass points. And the way that we execute the mass points technique is by setting certain points on multiple line segments as certain masses, so that when you think of them as points being balanced on a seesaw, you can imagine them as like masses being added together such that they balance on both sides. So in other words, if say that you take a segment AB, for example, and you have a point, let's say C in the middle. Let's say, for example, we put a mass of 2 at point A and a mass of, let's say, 5 at point B. The two masses both together have to balance in there. So the mass in the middle has to be the sum of the masses at A and B, which is 7, since 2 plus 5 is 7. And in order to have the masses balance the center, we have to make sure that both of the points are at appropriate distances from the center mass. And since point A has mass 2 and point C has mass 7, the difference between the two masses is 5. And the difference between the masses 7 and 5 at C and B respectively is 2. So the ratio from AC to BC is 5/2. And the ratios play out like this in order to balance out the masses such that we create an appropriate center of mass at the right distances from each of the 2 points at the ends of the line segment. So now, looking back at the original problem and the original diagram, let's try applying the mass points technique to segment AB. Since we know from the angle bisector theorem that AL over BL is 3/2, let's try playing around with mass points here. So we see that AL is the longer of the two segments AL and BL. Therefore, we must have a smaller mass at point A. So if we look at the fraction 3/2, we see that the numerator and denominator are relatively prime. So we can set a mass of 2 at point A, leaving us with a mass of 3 at point B. And the center mass, L, must be the sum of the two masses at A and B. So the mass at point L must be 5. And if we want to double check this, we see that AL to BL is 3/2, as we can see from the difference with the masses 5 minus 2 all over 5 minus 3. Now, next let's look at segment AC. We see that AK is congruent to CK since K is the midpoint of AC. So, since K is the midpoint of AC, it must be equidistant from points A and C, and thus the mass at point C must be the same as the mass at point A, so the mass at point C would also be 2. And that leaves us with the mass at K equal to 4. Now, next let's look at segments BK and CL. We see that the sum of the masses of the endpoints of both of those line segments is equal to 3 plus 4, or 5 plus 2, which is equal to 7. So the mass at point P must equal 7. Now, looking at the masses again, especially at segment CL, we see that the ratio from CP to LP is equal to 7 minus 2 all over 7 minus 5, since we're looking at the differences between the masses, and so we use that to calculate the ratio distances. And so the ratio from CP to LP is 7 minus 2 over 7 minus 5, which is 5 over 2. And here we see that CP is equal to 180 degrees. No, sorry, 180. So 180 over LP is equal to 5 over 2. Now the original problem statement asks us to find LP, so we just had to solve this proportion. So cross multiplying gives us 5LP equal to 180 times 2, which is 360. And dividing both sides by 5 gives us LP equal to 360 divided by 5, leaving us with an answer of 72.